It all began with that fateful moment when a sophisticated spacecraft, with impeccable precision, commenced a journey unlike any humanity had undertaken before. The Voyager 2 spacecraft was more than just an engineering marvel. It was humanity's first emissary sent to distant planets, a silent explorer tasked with uncovering the profound mysteries of worlds whose existence we could barely surmise. Its path led it past colossal gas giants and icy moons, revealing environments that, with their incomprehensible strangeness, seemed almost alien. The information transmitted back to Earth forever changed our perception of these remote celestial bodies. Voyager showcased Jupiter's raging storms, the intricate structure of Saturn's rings, and Neptune's supersonic wind currents. However, it was the fleeting encounter with Uranus, the least explored of the gas giants, that left us with the deepest enigmas. Mysteries carefully hidden within the planet's magnetic field, its natural satellites, and its unusual asymmetrical axial tilt. Voyager's journey may have concluded many decades ago, but its discoveries still resonate with the questions we ask today. And now, by reanalyzing its data with modern technology and new scientific approaches, we are uncovering features of these worlds, especially Uranus, that Voyager itself could never have imagined. The flyby of Uranus by NASA's Voyager 2 spacecraft in 1986 marked a significant milestone in our exploration of the outer solar system. For the first time, we had a unique opportunity to observe this distant, enigmatic planet up close. Its characteristic blue-green hue, faint rings, and an axial tilt so unique that Uranus orbits the Sun like a rolling ball. However, hidden beneath the impressive images and data collected during this momentous encounter are findings that suggest our understanding derived from Voyager's observations, particularly concerning its magnetosphere, may require revision and refinement. Voyager 2's journey to Uranus occurred under highly atypical conditions. The spacecraft arrived just days after a rare and extremely powerful burst of solar wind, a high-energy stream of charged particles emanating from the Sun, which compressed the planet's magnetic field to a tiny fraction of its usual size. The solar wind is a constant flow of charged particles emitted by the Sun, which typically shapes the magnetic environments of planets, creating what are known as magnetospheres, protecting worlds from harmful solar radiation. But in this specific instance, the intensity of the solar wind was so colossal that it compressed Uranus's magnetosphere to approximately 20% of its normal volume, significantly distorting the data the spacecraft could collect. According to a recent scientific study published in the reputable journal Nature Astronomy, such circumstances are extremely rare, occurring only about 4% of the time. Had Voyager arrived a week earlier, it would have observed a much larger magnetosphere, more consistent with those of other gas giants like Jupiter, Saturn, and Neptune. Previously, scientists believed that Uranus's magnetosphere was unusually weak, characterized by a low plasma concentration and high-energy radiation belts. Plasma, a distinct state of matter where atoms break down into charged particles, is a common feature of other planetary magnetospheres, especially those with strong magnetic fields. The data obtained by Voyager suggested that Uranus's magnetosphere experienced a severe deficiency of plasma originating from the solar wind and its moons, leaving its plasma environment abnormally sparse. However, a new, more in-depth analysis points to a completely different conclusion. The solar wind likely suppressed the presence of plasma in the planet's magnetosphere, leading to the erroneous belief that Uranus was devoid of significant plasma. By re-evaluating the data in light of the extraordinary intensity of the solar wind, scientists discovered a serious error in the previous interpretation. They now believe that Uranus's magnetosphere is much more similar to those of other gas giants than previously thought. Furthermore, this research has fundamentally changed our understanding of Uranus's moons, Titania and Oberon. Previous Voyager observations indicated that these moons orbited outside the planet's magnetosphere. Now, researchers suggest that these moons are likely located within the protective bubble of the magnetosphere, which could have significant implications for understanding potential subsurface oceans on these moons, a growing area of scientific interest as scientists continue to actively explore the possibility of life in the outer solar system. Now, let's take a closer look at what we know about the solar wind. When these energetic charged particles interact with a planet's magnetic field, they exert pressure that can cause the magnetosphere to compress, expand, or even change shape. This interaction is by no means static. Solar wind conditions continuously transform under the influence of key factors such as solar activity and the planet's distance from the central star, the Sun. On planets with powerful magnetic fields, such as our Earth, Jupiter, and Saturn, the solar wind significantly affects their magnetospheres, forming protective shields that guard the planet from harmful radiation. The magnetosphere, in essence, represents a planet's protective system, formed by its internal magnetic field. It acts like a shield, effectively deflecting and redirecting streams of charged particles. However, this system is not impenetrable. Its strength and size largely depend on the dynamic pressure of the solar wind, which is characterized by variable intensity and speed. During the period when the Voyager 2 spacecraft made its flyby of Uranus in 1986, conditions were extremely extreme, as the solar wind's dynamic pressure reached its peak. The dynamic pressure of the solar wind results from the product of the solar wind's mass density and the square of its velocity. Under normal conditions, Uranus's magnetosphere extends approximately 22 to 25 planetary radii from it. However, during the flyby, the magnetopause, the boundary where the solar wind pressure balances the planet's magnetic pressure, was compressed to 17.3 Uranian radii. As solar wind pressure increased in the days leading up to the flyby, the magnetosphere's size significantly decreased. This compression not only affected the magnetopause, but also, quite likely, impacted the unusual behavior of the planet's radiation belts. Typically, radiation belts around planets are formed from plasma originating from the planet's atmosphere, its natural satellites, and the solar wind. The intense solar wind during Voyager's approach likely pushed plasma out of Uranus's magnetosphere, leaving this region depleted and altering the typical behavior of its radiation belts. This resulted in an unexpectedly intense electron radiation belt, which puzzled scientists for decades until new discoveries emerged this October. So, what do we know? The unique nature of Uranus, revealed during the Voyager 2 flyby, had long been a puzzle for scientists. Data from the spacecraft indicated an unusually tilted and offset magnetic field, contributing to the perception of Uranus's magnetosphere as extreme and unlike any other in the solar system. However, subsequent studies have demonstrated that this interpretation does not fully reflect the true dynamics of the planet's space environment. A compression of the magnetosphere, similar to what was observed at Uranus, is not a static change. It initiates a cascade of dynamic processes. The increased dynamic pressure of the solar wind led to the injection of hot plasma from the magnetotail into the inner magnetosphere. This process is analogous to what has been observed on other planets, such as Saturn, where solar wind compression events enhance kilometric radiation and cause magnetic field reconfigurations. For Uranus, the result was a more intense electron radiation belt and significant changes in the plasma composition of its magnetosphere. Interestingly, the intense solar wind conditions likely caused Uranus's magnetosphere to behave similarly to those of other gas giants, such as Jupiter and Saturn. As the magnetosphere compressed, the radiation belts could have become more charged, similar to what happens during geomagnetic storms on Earth. This phenomenon is well documented on Saturn, where magnetosphere compression increases electron radiation. On Uranus, a similar event could have enhanced the electron flux in the radiation belts, even though the planet's environment was previously thought to be almost devoid of plasma. The increase in radiation during this compression event could also have caused changes in magnetotail dynamics, such as magnetic reconnection. This well-known process, observed on planets like Earth and Saturn, could have ejected plasma from the magnetotail into the inner magnetosphere, further altering plasma density and radiation levels. For example, Similar events on Saturn have been linked to the intensification of radiation belts and auroral activity. However, the behavior of Uranus's magnetosphere under such extreme solar wind conditions proved not entirely predictable. Although the scientific community has a significant amount of information on how various planetary magnetospheres respond to compression, the pronounced tilt of Uranus's magnetic field and its asymmetric structure significantly complicate these interactions. Uranus's unique axial tilt can form specific magnetospheric configurations that may contribute to the observed enhancement of electron flux and the unusual behavior of its radiation belts. Now that scientists have revisited the dynamics of Uranus's magnetosphere, it has become critically important to understand how these conditions impact the likelihood of subsurface oceans on the planet's moons. Uranus's outer moons, namely Titania and Oberon, have always sparked keen interest among researchers, especially in the context of potentially having subsurface oceans. These celestial bodies orbit Uranus at distances of 17 and 22.8 Uranian radii respectively, placing them in a unique position relative to the planet's magnetosphere. For moons located within the magnetosphere, such as Miranda, Ariel, and Umbriel, the detection of any subsurface oceans is more likely to be achieved using the magnetic induction method. This is because the planet's magnetic field will generate electrical currents in the moon's conductive layers, which, in turn, will produce measurable responses. However, Titania and Oberon present a different challenge. Their location near or slightly outside the magnetopause, which is the boundary between Uranus's magnetic influence and the surrounding solar wind, reduces the likelihood that these moons will experience the same level of magnetic interaction. Earlier studies suggested that Titania and Oberon might remain outside the magnetosphere for significant portions of their orbits. Such a position would hinder the detection of any subsurface oceans, as these moons would be exposed to the solar wind and the magnetosheath, a turbulent region located between the magnetosphere, virtually precluding the possibility of magnetic induction measurements. Nevertheless, new data indicate that Titania and Oberon appear to remain within the magnetosphere for most of their orbital paths. According to simulation results, Titania has less than a 4% chance of crossing the magnetopause, while the probability for Oberon is slightly higher, approximately 13%. This means that, contrary to previous assumptions, these moons are generally located within Uranus's protective magnetic bubble. This discovery significantly impacts the prospects for detecting subsurface oceans, as the moons remain protected by the magnetosphere for most of their orbits. Thus, the potential for applying the magnetic induction method becomes much more feasible than previously thought, opening new avenues for further research. This finding also carries important implications for plasma interactions between the moons and the planet's magnetosphere. While the magnetosheath typically represents a solar wind-dominated plasma environment, the orbits of moons located within the magnetosphere imply that they primarily interact with magnetospheric plasma. This interaction is likely to be far less disruptive to magnetic induction measurements, significantly facilitating the task for future missions to detect any subsurface oceans. Science is never static. It is a continuous process characterized by discoveries, refinements, and sometimes adjustments to previous understandings. The case of Uranus vividly demonstrates how newly acquired data can challenge established assumptions, prompting us to reevaluate what we once considered definitively known. However, to truly comprehend the nature of this distant planet, we must return to it, armed with the latest technologies. A future orbital mission could provide continuous, high-resolution data, allowing for a more detailed study of the planet, its moons, and its ring system. As preparations for future missions to the Uranian system advance, new insights into the positions of Titania and Oberon within the magnetosphere become critically important. Furthermore, a deep understanding of solar wind dynamics and magnetospheric variability will influence the planning of flight trajectories, ensuring spacecraft arrive at optimal times for data collection. Magnetic induction studies, successfully applied to other icy moons like Europa and Enceladus, can now be applied to Titania and Oberon with greater confidence. A mission specifically targeting these moons could use magnetic sensors to probe their internal structures for liquid water beneath their icy shells. Such a mission is also capable of filling in missing pieces of the puzzle, significantly expanding our understanding of worlds located in the outer solar system. The future of outer solar system exploration is becoming increasingly clear. Leading global space agencies and new players in the space arena are actively focusing their attention on missions directed toward Uranus and its numerous moons. In 2022, a Uranus orbiter and probe were included on NASA's highest priority list within the Decadal Survey for Planetary Science, covering the period from 2023 to 2032. This strategic decision underscores the growing importance of comprehensive study of the ice giants, which remain largely unexplored and mysterious objects. It is anticipated that a specialized spacecraft, whose primary objective will be to study the plasma environment, radiation structure, and evolutionary processes of the Uranian system, will be launched in February 2031, reaching Uranus by 2043. The spacecraft's main focus will be on investigating the planet's plasma, its magnetic fields, and the heliophysical environment, providing critically important data on the dynamic processes governing the ice giants. The arrival of this mission will be a truly pivotal moment in the history of Uranus exploration. The spacecraft will have a dry mass of about 1 metric ton and, in addition to its key tasks, will also collect data on Uranus's atmosphere and rings. The launch window for this mission is open between 2030 and 2034. The People's Republic of China is also actively entering this promising field, with its ambitious Tianwen-4 mission aimed at Jupiter and Uranus, scheduled for launch in 2030. Tianwen-4 will carry 2 separate spacecraft aboard a Long March 5 rocket. One of the probes will head to Jupiter's moon Callisto, while the other will perform a flyby of Uranus. This grand mission will mark China's first exploration of the ice giants. The spacecraft, though smaller in mass than the NASA mission, will also be equipped with high-precision instruments designed to study Uranus's magnetosphere, and will journey into the outer solar system using a series of gravity assists to gain the necessary momentum. The achievements of the Voyager missions in exploring the outer planets have undoubtedly paved the way for future great discoveries. But the true path to a profound understanding of the cosmos lies in our boundless curiosity and relentless exploration. As we continue to gaze at the stars, their majestic legacy inspires us to new endeavors, forming a strong foundation upon which humanity builds its comprehensive understanding of the universe. In the boundless expanse of space, amidst countless stars and galaxies, an almost imperceptible whisper can be heard. It is the whisper of a distant star that has traveled light years to reach us here on Earth. This is not merely a science fiction tale, but a tangible reality of our universe, a vivid testament to our ever-growing understanding of the cosmos. Scientists, carefully listening in on space, have detected a remarkable signal, a radio wave from a star system not so different from our own. The star, known as YZ Ceti, is located just 12 light-years away. But this is no ordinary signal. It carries the potential signature of a magnetic field, much like the one that reliably protects our own planet. A magnetic field that may envelop an Earth-sized rocky exoplanet orbiting YZ Ceti. What could this mean for us? Could this distant world be far more similar to ours than we ever imagined? And what might it tell us about the fundamental search for life beyond our solar system? Let us journey light years to delve deeply into the mysteries of radio signals in space and meticulously investigate the magnetic fields of distant worlds. In the infinite silence of space, radio signals can, without exaggeration, be characterized as whispers. But what are these signals, and how are they able to travel such immense distances through space? Radio signals are a type of electromagnetic radiation, similar to light, X-rays, or microwaves. They are generated by diverse sources, from giant stars and entire galaxies to human-made satellites and spacecraft. These signals propagate at the speed of light, carrying invaluable information across vast cosmic distances. They can tell us about the chemical composition of stars, the presence of planets, and even the very origin of the universe. But how do we detect these elusive signals? The answer lies in the advanced technology of radio astronomy. Radio telescopes, such as the Very Large Array in New Mexico or the now-defunct Arecibo in Puerto Rico, are specifically designed to detect and meticulously analyze radio signals arriving from space. They serve as our ears for the cosmos, carefully listening for faint whispers emanating from the depths of the universe. Once a signal is detected by a radio observatory, it undergoes rigorous analysis using sophisticated algorithms and computer models. This analysis can provide extensive information about the signal's source, from its precise location and distance to its fundamental physical properties.
However, radio signals reaching us from cosmic distances are not merely a subject of scientific inquiry. They also possess significant practical applications. For instance, these signals, broadcast by satellites, form the fundamental basis for global positioning systems, better known as GPS navigation, as well as for accurate weather forecasting and continuous monitoring of our planet's surface. Thus, they have become an integral component of our modern technological infrastructure. The next time your gaze turns to the starry night sky, remember, a symphony of signals is unfolding there, an unseen cosmic dialogue, a grand orchestra that we are only just beginning to comprehend. Let's return to the constellation Cetus, the majestic sea monster, within whose depths lies a star sending us its silent messages across boundless light years. Its name is YZ Ceti. YZ Ceti is a red dwarf, a celestial body significantly smaller and cooler than our Sun. It is located 12 light-years away from us, making it a relatively close neighbor by cosmic standards. However, the true allure of YZ Ceti lies not so much in the star itself, but in the objects orbiting it. At least 3 exoplanets are known to orbit YZ Ceti, and among them, the innermost one, designated YZ Ceti b, is of greatest scientific interest. YZ Ceti b is a rocky exoplanet, comparable in size to Earth, orbiting extremely close to its parent star. Its proximity to the star is so great that its year, the time it takes to complete one full orbit around YZ Ceti, is only 1.6 Earth days. Recently, using the capabilities of the Very Large Array, a team of scientists from Bucknell University, including Professor Jackie Villadsen and her colleague J. Sebastian Pineda, detected a repeating radio signal originating from the YZ Ceti system. This signal was recorded at a frequency between 2 and 4 gigahertz. It appears to be modulated by both the star's rotation and YZ Ceti b's orbital motion, directly indicating an interaction between the star and the planet's magnetic field. This discovery could have far-reaching implications for our understanding of exoplanets and the nature of their magnetic fields. Although the probability of life existing on YZ Ceti b is extremely low due to its extreme proximity to the star, the detection of its magnetic field is a significant event, as it opens a promising method for identifying more potentially habitable worlds in the future. But what does this signal truly mean, and why do magnetic fields play such a crucial role in our ongoing search for extraterrestrial life? To answer these pressing questions, we need to delve into the invisible force fields that shape and define our universe. Magnetic fields represent a fundamental force of nature. They guide the compass needle, helping travelers find their way, assist birds in orienting during their long migrations, and reliably protect our planet from the destructive effects of the solar wind. However, magnetic fields are not exclusively an earthly phenomenon. They also play a key role beyond Earth's boundaries. Our Sun, for example, possesses a complex and dynamic magnetic field. It controls all solar activity, from the formation of sunspots to powerful solar flare eruptions. Magnetic fields also shape the structure of galaxies, guiding the movement of interstellar gas and influencing the formation of new stars. But perhaps the most intriguing role of magnetic fields in space lies in their potential impact on planetary habitability. A powerful magnetic field can reliably shield a planet from harmful radiation from its star, helping to maintain a stable atmosphere and, possibly, even creating conditions favorable for the emergence and development of life. This is why the detection of a potential magnetic field on exoplanet YZ Ceti b generates such immense interest. It can provide invaluable information about the planet's atmosphere and its potential to support life. How do magnetic fields affect the detection and subsequent interpretation of signals from space? To grasp this relationship, we need to delve a little deeper into the nature of radio signals and magnetic fields. Radio signals are a type of electromagnetic wave, meaning they consist of oscillating electric and magnetic fields. These fields can interact with other magnetic fields they encounter on their journey through the vastness of space. When a radio signal passes through a magnetic field, it can be altered in various ways. Its direction can be deflected, a phenomenon known as deviation. Its polarization, meaning the orientation of its electric field, can be rotated. Its frequency, meaning the number of waves passing through a certain point per unit of time, can be shifted. These transformations can provide invaluable information about the magnetic field that caused these changes. By studying these changes, scientists can deduce the properties of the magnetic field, such as its strength and spatial orientation. However, magnetic fields can also create certain difficulties for detecting signals from space. They can cause interference, making it harder to detect a useful signal. They can distort the signal, making its interpretation more complex. This is why the study of magnetic fields is so important in radio astronomy. By understanding how magnetic fields affect radio signals, scientists can develop effective methods to correct for these effects and extract valuable information hidden within the signals reaching us from cosmic depths. To more deeply understand the influence of magnetic fields on creating favorable conditions for the genesis and sustenance of life on a planet, let's turn our gaze closer to home, to a familiar reddish neighbor in our cosmic backyard, Mars. The red planet has long captivated our imagination with its majestic volcanoes, deep and extensive canyons, and hints of liquid water. It undoubtedly represents one of the most intriguing places in our entire solar system. However, Mars also holds a certain enigma. Unlike Earth, Mars possesses an extremely weak and highly heterogeneous magnetic field. This circumstance has very serious consequences for the planet's atmosphere and consequently for its ability to support life. Mars's magnetic field is not generated by a dynamo effect in its core, as is the case on Earth. Instead, it represents residual traces of magnetism trapped in the planet's crust from those distant times when Mars did indeed possess a global magnetic field. Without the reliable protection of a strong magnetic field, Mars's atmosphere is directly exposed to the solar wind, a powerful stream of charged particles continuously emitted by the sun. Moreover, the latest models presented by R. Sakata from the University of Tokyo and other researchers suggest that a weak magnetic field, similar to what is observed on Mars after its dynamo completely shut down, may actually lead to an even faster atmospheric loss than in the complete absence of a magnetic field. Simulations vividly demonstrated that a weak magnetic field contributes to the fastest loss of atmospheric ions, 6 times faster than with no magnetic field at all. The reason for this lies in the fact that the field lines of a weak magnetic field were easily pushed away by the solar wind, creating a kind of path for ions to escape unimpeded into space above Mars's night side. This suggests that Mars's remaining magnetic field may have even accelerated the planet's transformation into the cold and barren world we see today. Over billions of years, this process led to Mars losing most of its atmosphere, a phenomenon known as atmospheric escape. This fundamentally changed Mars, transforming it from a potentially warm and wet world in its early history into the cold and arid planet we observe in our time. The case of Mars vividly and clearly illustrates the critical importance of magnetic fields for the habitability of any planet. It shows us that without a strong magnetic field, a planet, even one as Earth-like as Mars, can irreversibly lose the conditions that make it suitable for life, an atmosphere and water. Incidentally, we have already extensively discussed the challenges and potential solutions aimed at making Mars a second home for humanity in a separate video. Exoplanets, planes that orbit stars outside our solar system, have recently become a key focus of astronomical research. To date, over 1,000 such planets have been discovered, opening up a multitude of unique opportunities for studying the incredible diversity of planetary systems existing in our galaxy. One of the most exciting developments in this field was the detection of the first known magnetic field on an exoplanet in late December 2021 by an international team of astronomers using the Hubble Space Telescope for their investigations. It was detected on a Neptune-sized planet named HAT P11b. HAT P11b is located approximately 123 light-years away from us in the constellation Cygnus. It is a hot Neptune, a specific type of exoplanet that is similar in size to Neptune but orbits significantly closer to its star, resulting in extremely high surface temperatures on the planet. The discovery of a magnetic field on HAT P11b was a truly groundbreaking finding. It convincingly demonstrated that exoplanets are capable of generating their own magnetic fields, just like the planets in our solar system. As mentioned earlier, studying exoplanet magnetic fields can provide invaluable information about their internal structure, atmospheric properties, and, most importantly, their potential habitability. For example, a strong magnetic field can reliably protect a planet's atmosphere from the destructive effects of stellar winds, thereby helping to preserve conditions that could favor the sustenance of life. This brings us back to YZ Ceti, the exoplanet from which a signal was recently detected. If this signal indeed indicates the presence of a magnetic field, it could have very serious implications for our understanding of this exoplanet and its potential for the emergence and development of life. Throughout our wondrous journeys across the boundless expanses of space, stretching from the well-studied landscapes of Mars to the distant reaches of the YZ Ceti system, humanity has profoundly recognized the invisible yet powerful force of magnetic fields. Their colossal influence on planetary formation and their potential for the emergence and sustenance of life have become evident. In the past few years, the field of studying signals emanating from other galaxies has experienced rapid growth. For instance, the giant Meteorwave radio telescope, located in India, managed to pick up an extremely faint signal from the most distant galaxy discovered to date. The signal detected in the YZ Ceti system has opened yet another completely new window into the uncharted universe, thereby reminding us once again how many mysteries still await unraveling about our world. Looking ahead, it should be noted that the study of signals from other galaxies will invariably remain at the forefront of space research. Every such signal carries the potential for entirely new discoveries. Therefore, when we turn our gaze to the night sky, let us always remember that we are observing not just stars and galaxies. We are looking at a universe teeming with invisible forces, subtle whispering signals, and boundless hidden possibilities. And as we continue to listen intently and actively explore, who knows what amazing discoveries may await us? In the boundless expanse of our solar system lies a great mystery, the pulsating source of energy and life itself, our Sun. For 10 years, the Cosmic Sentinel, NASA's Solar Dynamics Observatory, or SDO, has been our vigilant eye, closely observing this fiery celestial giant. This unique mission, successfully launched into space on February 11, 2010, embarked on a true odyssey not merely for superficial observation, but for deeply unraveling the numerous mysteries of our closest star. Just imagine a world where every second reveals a history millions of years old, where colossal plumes of fire, sometimes exceeding the size of Earth itself, erupt from the Sun's surface. This is the world the Solar Dynamics Observatory explores, a world where a new image is captured every 75 seconds, each an integral piece of a vast puzzle in understanding the Sun's comprehensive influence on our solar system. As we journey through a decade of solar observations, we immerse ourselves in an astonishing realm where colossal waves ripple across the Sun's surface, where plasma eruptions challenge our current understanding of physics, and where the solar cycle powerfully resonates throughout the solar system. This is not merely a tale of a satellite and a star. It is a captivating story of discovery, overcoming challenges, and the relentless pursuit of knowledge. Our fascinating journey with the Solar Dynamics Observatory begins with a momentous event: its launch on February 11, 2010. Amidst the thunderous roar of engines and the fiery ascent of the Atlas V rocket, the Solar Dynamics Observatory commenced its vital mission to explore the deepest mysteries of the Sun. This launch marked not only the beginning of the mission itself, but also the dawn of an entirely new era in solar observations. Once in space, the Solar Dynamics Observatory successfully entered a geostationary orbit, positioned to have an unobstructed and continuous view of the Sun. Its primary goal is to understand the Sun's comprehensive influence on Earth and the entire solar system by meticulously studying the solar atmosphere with unprecedented detail. Central to this mission is a suite of sophisticated instruments on board the Solar Dynamics Observatory, each specifically designed to study different aspects of the Sun's behavior. Among them, the Atmospheric Imaging Assembly, or AIA, stands out. This remarkable instrument captures images of the solar atmosphere at various wavelengths, each revealing different features of the Sun. AIA's capabilities are truly revolutionary. It observes the Sun at 10 different wavelengths, each precisely tuned to a specific temperature of solar material. This allows scientists to view the Sun's surface and atmosphere across a wide spectrum of colors, with each color revealing unique and previously unknown phenomena. AIA's observations have played a crucial role in advancing our understanding of solar dynamics, from cooler, darker sunspots to blazing hot coronal loops. Over the past decade, it has relentlessly observed the Sun, capturing over 425 million high-resolution images, each contributing to a continuous stream of data, painting a vivid and dynamic portrait of the Sun's ever-changing behavior. Why do we study the Sun with such diligence and persistence? The answer lies in the profound and pervasive influence of the Sun on our system. It is the indispensable heart of our cosmic environment, controlling processes ranging from Earth's auroras to weather conditions on other planets. Understanding the Sun means deeply comprehending the fundamental processes that govern our corner of the universe. Through AIA's eyes, we have watched the Sun's story unfold in real time. Ejections of solar material, twisting magnetic fields, and the intricate dance of solar flares, all captured in stunning detail. AIA didn't just open a window into solar activity. It paved the way for a deep understanding of the complex interactions that drive space weather. This decade of observation has revealed the dynamic nature of the Sun with unprecedented detail, from the ebb and flow of solar flares to the mysterious 11-year solar cycle. The Solar Dynamics Observatory has provided invaluable information about phenomena that were once merely scientific speculation. The mission has witnessed previously unfathomable solar events. In the boundless expanse of space, the Solar Dynamics Observatory, or SDO, like a vigilant guardian, tirelessly records every minute detail of the Sun with unprecedented precision. Over its 10 years of fruitful activity, SDO has amassed an impressive collection totaling over 425 million high-resolution images. This colossal database forms a continuous visual narrative of our star's ever-changing face. One can only imagine a world where every fraction of a second reveals a completely new aspect of a star. This is precisely how SDO functions, capturing images of the Sun every 75 seconds. This relentless pace of observation grants humanity the opportunity to witness the dynamic nature of the Sun virtually in real time, capturing processes and transformations that, until very recently, remained beyond our perception. SDO's unique ability to observe the Sun at various wavelengths has opened fundamentally new horizons for a comprehensive study of our star. Each wavelength, like a key, unlocks a door to a unique layer of the solar atmosphere, from its turbulent surface to the outermost boundaries of the corona. This multi-wavelength approach allows us to comprehend the Sun in all its diversity and splendor. Among the multitude of wavelengths meticulously investigated by SDO, the extreme ultraviolet wavelength of 17.1 nanometers deserves special attention. This specific wavelength provides scientists with an invaluable and unparalleled view of the solar corona, the outermost layer of its atmosphere. The corona is the epicenter of solar activity, where temperatures reach millions of degrees Celsius, and where the unsolved mysteries of such grand solar phenomena as coronal mass ejections and powerful solar flares are hidden. Through the lens of SDO, the corona no longer appears as a mysterious and dark region, but as a bright, dynamic, and energy-filled environment. We can observe coronal loops, giant arcs of plasma driven by the Sun's powerful magnetic field, and witness grandiose eruptions that send waves of solar material far into space. These observations are not only captivating in their visual beauty, but also serve as a cornerstone for understanding how the Sun influences space weather and, as a consequence, our own planet. As humanity continues its studies of the Sun with SDO, every image captured and every observation at each wavelength steadily enriches our understanding of our star's enigmatic corona, revealing a dynamic and incredibly complex celestial body as never before. Embarking on the quest to unravel the 11-year solar cycle, the Solar Dynamics Observatory has been at the forefront of solar science. This cycle, a cosmic rhythm that has puzzled astronomers for many years, is characterized by periodic changes in solar activity, including the frequency of sunspots, the intensity of solar flares, and the number of coronal mass ejections. SDO's decade-long observations encompass almost a complete solar cycle, offering scientists a front-row seat to the Sun's ever-changing dynamics. During solar maximum periods, the Sun appears as a seething hive of activity, abundant with sunspots and erupting with powerful solar flares. Conversely, during solar minimum, the Sun enters a quieter phase, characterized by fewer sunspots and reduced surface activity. Throughout its mission, SDO has witnessed and meticulously recorded numerous solar events. Incredible plasma ejections, known as coronal mass ejections, have been captured in minute detail, revealing the colossal energy unleashed during these grandiose events. Solar flares, intense bursts of radiation, have been observed across various wavelength ranges, providing invaluable information about the mechanisms that trigger these explosive phenomena. In addition to this captivating spectacle, SDO has also witnessed rare and mesmerizing planetary transits across the Sun's surface. These events, while fascinating in themselves, serve a more important purpose in solar science. They offer unique opportunities to study the Sun's atmosphere and its interactions with other celestial bodies, further expanding our understanding of solar dynamics. In the exploration of space, challenges are inevitable and manifold. NASA's Solar Dynamics Observatory has encountered its fair share of obstacles, each testing the mission's resilience and ingenuity. From Earth shadows and lunar eclipses to technical difficulties, such as the problem with the Atmospheric Imaging Assembly (AIA) instrument in 2016, SDO's path has been arduous and winding. One of the constant and unavoidable challenges regularly faced by the Solar Dynamics Observatory, or SDO, are the periodic occultations caused by the Earth and Moon. These natural celestial bodies, while an integral part of SDO's natural orbital path, temporarily limit its ability to observe the Sun unimpeded. Earth-induced eclipses, occurring predominantly during the equinoxes, cast a broad shadow over the space observatory, leading to brief periods of complete darkness and interrupting the continuous transmission of valuable scientific data. Similarly, lunar transits, though quite rare, momentarily block SDO's view of the Sun, creating a unique yet challenging scenario for conducting precise solar observations. In 2016,
SDO encountered a rather serious technical problem when its key research instrument, the Atmospheric Imaging Assembly, or AIA, experienced a malfunction. This unexpected anomaly jeopardized one of the most crucial data streams obtained during the mission. AIA, responsible for capturing high-resolution images of the solar atmosphere, is an integral part of our understanding of the Sun's dynamic and ever-changing behavior. The problem that arose with AIA was complex and involved the detection and subsequent analysis of invisible coronal mass ejections, or CMEs. CMEs, which occur at high altitudes in the solar corona and in regions with weak or scattered magnetic fields, are admittedly extremely difficult to observe. Unlike typical CMEs, which manifest as visible darkenings or brightenings on the Sun's surface, hidden CMEs can often only be detected with specialized instruments, such as a coronagraph. Resolving the problem with AIA required coordinated and intensive efforts from both engineers and scientists. The team applied innovative methods for visualizing remote sensing data obtained by AIA. By comparing different images, current images of the Sun with images taken 12 hours earlier, the team was able to capture slow but significant changes in the lower corona. This innovative method revealed subtle, previously unnoticed changes in the Sun's magnetic fields and plasma loops. To further enhance the visibility of these subtle changes, advanced image processing techniques were applied, including wavelet packet alignment and multi-scale Gaussian normalization. These methods allowed the team to detect darkenings, which are key indicators of CMEs, and to gain a more complete and comprehensive understanding of solar events. Delving into the implications of the discoveries made by the Solar Dynamics Observatory, we find the profound and pervasive influence of the Sun not only on Earth, but also on the wider, boundless expanses of space. Decades of continuous observations conducted by SDO have significantly advanced our understanding of space weather and its numerous, far-reaching consequences for our planet and beyond. Space weather, an overarching term for the Sun's energetic activity, includes phenomena such as powerful solar flares, large-scale coronal mass ejections, and high-energy solar energetic particles. These events, born from the Sun's dynamic surface and atmosphere, can propagate through space, affecting both planets and spacecraft. Regarding Earth, the effects of space weather are intriguing and far-reaching. The interaction of solar wind and coronal mass ejections with Earth's magnetosphere can lead to spectacular and mesmerizing auroras, widely known as the Northern and Southern Lights. However, these interactions can also have more disruptive consequences, such as disruptions to satellites, communication systems, and even extensive power grids. SDO's discoveries have played a significant role in enhancing our ability to forecast space weather events. By understanding the complex mechanisms that cause solar eruptions and their trajectories, scientists can better predict when and how these events might affect Earth. Such forecasting is crucial for preparing and protecting our technological infrastructure, both in space and on Earth. Beyond Earth, the implications of SDO's research extend throughout the solar system. Understanding space weather is vital for ensuring the safety of astronauts in space, as well as for the meticulous planning and successful execution of interplanetary missions. As we venture deeper into space, whether to the Moon, Mars, or beyond, knowledge of the Sun's behavior becomes increasingly important. In summary, the implications of a decade of diligent observations carried out by the SDO mission are truly profound and possess far-reaching influence. This groundbreaking mission has not only contributed to a significant deepening of our understanding of phenomena such as space weather and its comprehensive impact on our planet Earth, but has also successfully laid a solid foundation for significantly safer and more effective space exploration for many decades to come. If we turn our gaze to the future of solar observations, we see that the horizon of research is filled with boundless hopes and immense potential. The modern era in solar research is marked by the emergence of a number of groundbreaking missions, among which the Parker Solar Probe and the Solar Orbiter stand out. The Parker Solar Probe, successfully launched in 2018,
has already been able to approach the Sun at a minimum distance, unattainable by any other spacecraft before. It ultimately plans to plunge directly into the solar corona to reveal its innermost secrets to us. The Solar Orbiter, a product of fruitful collaboration between the European Space Agency and the National Aeronautics and Space Administration, launched in 2020, is equipped with advanced instrumentation designed to provide a comprehensive view of the Sun's poles and its vast outer atmosphere, regions that have remained virtually unexplored until now. These advanced missions are equipped with state-of-the-art instruments specifically designed to study the Sun in entirely new and unique ways. The Parker Solar Probe's journey through the fiery solar corona promises to provide invaluable data on the fundamental processes that govern the solar wind and streams of solar energetic particles. In turn, the Solar Orbiter's unique orbit and its extensive suite of scientific instruments will provide a holistic and comprehensive view of the Sun's atmosphere, its powerful magnetic field, and the solar wind. Looking ahead, it can be confidently said that the future of solar observations holds truly brilliant potential. The opportunities for making new, revolutionary discoveries are as boundless as the Sun itself. We stand on the verge of unraveling the innermost secrets of the Sun's magnetic field dynamics, which will undoubtedly lead to a significantly better understanding of phenomena such as solar flares and coronal mass ejections. A deep study of the Sun's internal mechanisms may reveal even more about the workings of its 11-year solar cycle. As we continue to observe and meticulously study the Sun, we are on the threshold of a new era in solar science, which promises to illuminate the darkest corners of our understanding of the star that sustains life here on our planet Earth. In a world where a phenomenon as fundamental as gravity is often taken for granted, we have set ourselves an ambitious task: to unravel the hidden truths that lie behind the scenes of our everyday perception. Prepare for a deep dive into the most enigmatic mysteries that challenge our entire understanding of the world around us. What if the very essence of gravity, as we know and accept it, is nothing more than an elaborate illusion? Today, we dare to challenge every belief you hold as undeniable truth. Together, we can penetrate the veils of ordinary perception and uncover the mysterious secrets hidden at the very core of gravity's fundamental principles. In the 17th century, according to a widespread and popular legend, the distinguished scientist Isaac Newton observed an apple falling from a branch in his garden. He noticed that this apple fell straight down, as if under the influence of some invisible yet definite force, which subsequently inspired him to formulate the famous law of universal gravitation. What exactly does this truly revolutionary law describe? An ordinary apple, as it falls, gradually gains speed. The apple, like any other object on our planet, possesses mass, though it is significantly less than the mass of Earth itself. According to Newton's theory, the gravitational force arising between Earth and the apple is directly proportional to their masses and, at the same time, inversely proportional to the square of the distance separating these two objects. To put it even more concisely, all objects, without exception, possessing mass and energy, mutually attract each other and are in a state of free fall relative to more massive bodies. All of this finds its mathematical expression in a well-known formula. This formula is deciphered as follows: gravitational force equals the product of the primary body's mass and the secondary body's mass divided by the square of the orbital radius. Incidentally, it should be noted that Newton attempted to model gravity as a field that surrounds absolutely all material bodies. This mental model is still actively used today to explain the gravitational interaction occurring between all existing objects. According to Newton's third law of motion, the Earth should also move towards the apple, as it too possesses its own gravitational field, but it is so small that we cannot perceive it. This phenomenon can be explained using Newton's second law, force equals mass times acceleration, as it is impossible to obtain the same acceleration for objects with different masses, even when the same force is applied to them. However, not everything was so straightforward. Newton also hypothesized that gravitational force could influence celestial bodies, including our natural satellite, the Moon. Furthermore, the Moon has not yet fallen to Earth, not only due to its constant and rapid orbital motion, but also because of the gravitational interaction that weakens between massive objects located at a significant distance from each other. Newton was able to convincingly explain the dependence of planets' rotation around the Sun, driven by the gravitational force between them, using an imaginary experiment.
Imagine setting up a cannon on a mountaintop and firing a cannonball horizontally. It would inevitably fall vertically to Earth after traveling only a short distance. But if fired with very great force, for example, at a speed of up to 4,500 miles per hour, the cannonball would constantly be in a state of free fall and would never reach the surface. According to Isaac Newton, this is precisely the state in which our Moon, and indeed all other planets, even those beyond our solar system, reside. Thus, Newton concluded that gravity is a universal force for the entire universe, acting uniformly everywhere. Moreover, Newton's great law did not contradict, but rather organically complemented other fundamental laws, such as the three laws developed by the distinguished astronomer Johannes Kepler. These laws explained the motion of planets in the boundless expanses of open space with astonishing accuracy. Notably, the law of universal gravitation can be logically derived from each of Kepler's laws. Thus, in accordance with Kepler's first and second laws, each planet's orbit around a star is an ellipse, which inevitably means a constant change in the distance from the planet to the star. This includes both the closest point from the planet to the Sun, called perihelion, and the farthest point, known as aphelion, where the planet covers the same distance in the same amount of time. Newton's law, in turn, describes in detail the acceleration of massive objects depending on their distance from the star. In particular, the third law, which explains that an increase in orbital radius affects the period of rotation, is also explained in the same way. Furthermore, the force that holds planets in their orbits is proportional to the product of the masses of the Sun and the planet, and inversely proportional to the square of the distance between these two celestial bodies, precisely as it occurs between objects on Earth. However, despite its universality, Newton's law could not provide an exhaustive explanation for several important scientific observations. For example, although Newton's theory excellently described the motion of most planets around the Sun, it faced difficulties in explaining the orbit of one of them, Mercury. You may recall that Mercury has an unusual oval orbit, but that's not its most striking feature. Its closest point of approach is always located in different places and slowly shifts around the Sun. This process is called precession. While this phenomenon is characteristic of all planetary orbits, it is most pronounced and astonishing in Mercury. The precession of Mercury's orbit is 5,600 arcseconds per century when observed from Earth. But the planet's actual precession time is 5,557 arcseconds. These lost 43 arcseconds remain unexplained within Newton's theory. However, all this and much more finds its confirmation in another fundamental theory, considered the cornerstone of modern science: Albert Einstein's general theory of relativity. Almost 300 years after Newton's revolutionary discovery, Einstein presented the world with his innovative view on the concept of gravity in general relativity, or GR. GR was preceded by the special theory, in which Einstein described space and time as an inseparable phenomenon, as if absolutely everything in the universe moves simultaneously in time and space. In accordance with GR, he explained that massive objects are capable of curving space-time and thereby influencing other objects around them, and it is this curvature that is gravity. While Newton's theory was based on a simple falling apple, Einstein, to vividly explain his idea, imagined a person in a falling elevator. When falling, they do not feel their own weight, as both their body and the elevator fall at the same speed. However, when a person moves upward in an elevator, they feel acceleration, and it seems to them that the floor is pushing on them.
Nevertheless, if there are no windows in the elevator, the person cannot tell what they are experiencing from their perspective. Falling in a gravitational field, or moving at a constant speed in a small region of space-time. In Einstein's theory, this phenomenon is called the equivalence principle. In fact, if, according to Newton's law, a person falls due to gravitational force, then according to Einstein's theory, this happens due to the absence of a force pushing the person upward. That is, a force acts on the person, created by the elevator floor, but this is not gravity. This also means that we are always in a state of acceleration, unless we are in a state of free fall or inertial motion from our perspective. Thus, Einstein concluded that gravity and acceleration are one and the same, and therefore we are in a state of free fall until an obstacle appears in our path, which became the basis for understanding that gravity is not a force. This is a very unexpected assertion. Let's examine the theory of relativity in more detail. So, as we have already noted, according to Einstein, gravity is a geometric curvature of four-dimensional spacetime. Its property is not a force acting in space. Simply put, one might try to imagine spacetime as a two-dimensional fabric, in which massive objects, such as a planet and the sun, create funnels. But this is not an entirely accurate representation. It is better to imagine spacetime as a three-dimensional grid consisting of lines, geodesics, along which planets move in freefall. They are massive enough to distort the lines along which any objects move. This is why it may seem to us that, for example, celestial bodies attract each other. Theoretical physicist John Wheeler explained this idea quite simply. Space-time tells matter how to move. Matter tells space-time how to curve. We cannot directly observe the curvature, but we can see the effect of Einstein's gravity. For example, if a crew on the International Space Station flies directly next to Earth, they will move in a circle due to the curvature, although from their perspective it will seem that they are moving straight, but a large object prevents them from moving in straight lines. Furthermore, we can observe this phenomenon on Earth. If two people move from a significant distance towards the North Pole, they will meet as they approach it. No force would act on them. They would simply follow curved lines due to Earth's sphericity. A similar situation applies to light phenomena. Isaac Newton assumed that light rays, like all other objects, are subject to bending under the influence of the gravitational force of massive celestial bodies. Consequently, the actual location of a light source, such as a distant star, should differ from what we visually perceive. However, the modern scientific paradigm asserts that light has no mass, and here a legitimate question arises. How could it be influenced by large cosmic objects? Albert Einstein, in turn, proposed an explanation according to which light, like us humans, travels along so-called geodesic lines. Since, according to general relativity, these lines are deformed near massive objects, light changes its direction of motion, which, in essence, means that gravity does not directly affect light itself. Notably, Einstein's calculations demonstrated that the angle of light deflection was almost twice as large as predicted by Newtonian theory. Einstein's idea found its confirmation thanks to observations by astronomers Arthur Eddington and Charles Davidson during the solar eclipse that occurred in 1919. They compared the actual positions of stars with the image of light captured in photographs and were able to reliably establish that the angular deflection indeed amounted to approximately 1.75 arcseconds, precisely as calculated by Albert Einstein. In particular, the general theory of relativity can also answer the riddle of Mercury's anomalous orbit, since according to its calculations, the orbit of this celestial body shifts by 43 arcseconds due to the curvature of the spatial fabric. In addition, another convincing proof that gravity represents the curvature of spacetime is the phenomenon in which a light wave can lengthen and lose its intensity under the influence of massive objects. Thus, if an observer is inside an accelerating spacecraft, then in their perception, a light wave emitted from a lower point will appear lengthened relative to its original wavelength. This, in turn, will entail a change in the light's color spectrum from red to blue. This phenomenon is called the gravitational redshift of light and is not predicted by Newtonian gravity. In 2016, Professor Andrea Ghez led a research group to observe the blue star S0-2, which made a close pass by the Sagittarius A black hole. If Einstein's theory is correct, then the light wave emanating from this star should have changed its color to red from the scientists' reference point, and the star indeed glowed red, which once again confirmed Einstein's concept of gravity. Thus, Albert Einstein's gravitational model marked a true breakthrough in understanding the fundamental physical processes occurring in our vast universe. Currently, it has been confirmed, perhaps not by all tests of its reliability, and reveals many subtleties of space-time structure. Nevertheless, the Newtonian model can still pose a serious competitor to general relativity. For example, observing the rotation of disk galaxies in the 1930s, Danish astronomer Jan Oort first noticed that the rotation speed of stars at the periphery of such galaxies remains constant, although, according to classical notions, they should move significantly slower. The solution to this paradox is hypothetical dark matter, first described by astronomer Fritz Zwicky, which supposedly surrounds galaxies. According to current scientific estimates, about 70% of the universe consists of dark energy, 27% of dark matter, and only 5% of ordinary matter. However, despite dark matter being an important hypothesis for explaining this phenomenon and many others, such as the bullet cluster, its existence has not yet been precisely confirmed experimentally. On the other hand, a modified model of Newtonian gravity, known as modified Newtonian dynamics, or MOND, proposed by astrophysicist Mordechai Milgram, can explain the state of orbital rotation. It postulates the existence of different rules for objects with much smaller accelerations than those observed in our solar system. Milgram modified the gravity formula by introducing a constant a0, which defines a critical point for acceleration. Thus, if the acceleration caused by gravity reaches this critical point, then Newton's laws, which were valid until that moment, will be replaced by new laws introduced by general relativity, and the inverse square law that we observe in our solar system will cease to operate, which will equalize the acceleration, meaning it will not depend on the distance to the center. This theory effectively explains the movement of stars in many other galaxies without needing to postulate the presence of dark matter. However, it has several serious unresolved problems. For example, it cannot completely exclude the presence of dark particles, as galaxy clusters in Mond's analysis still suffer from a missing mass problem, which is successfully resolved by dark matter. Consequently, this theory, while offering an explanation for the orbital velocity phenomenon, particularly has shortcomings that are still effectively resolved by general relativity. Finally, a key problem associated with Einstein's theory of gravity lies in its fundamental incompatibility with quantum mechanics. The main contradiction between these crucial areas of physics stems from the fact that general relativity is based on the principle of causality, whereas quantum physics operates with categories of probability. Consequently, general relativity cannot be applied at the quantum level, and quantum mechanics, in turn, is unable to effectively describe macroscopic objects. After all, an observer knows the exact location and speed of a large physical object. For such objects, there is no state of superposition. The only way out of this situation appears to be the development of a new theory of quantum gravity that could simultaneously explain the interaction of both large objects and the smallest fundamental particles. Despite some unresolved questions, Einstein's gravitational model, repeatedly confirmed experimentally, still serves as the basis for current scientific research. Regardless of its age, we cannot confidently assert whether general relativity will meet the same fate as Newton's law of universal gravitation, but harmonizing its world model with other areas of physics is, without exaggeration, vitally necessary for all of science. Thus, since we do not yet have a new comprehensive theory of gravity, we can conclude with some certainty that gravity is not a force in the traditional sense. The observable universe spans 93 billion light-years, a distance that is difficult for human comprehension. Within this immense cosmic space reside over 2 trillion galaxies, each literally teeming with billions of stars. The scale of the universe is awe-inspiring. But what captivates us is not only its colossal size, but also its astonishing complexity. The cosmic web is a grand network consisting of galaxies and mysterious dark matter, forming a structure resembling a vast, interconnected web. Now, let us transport ourselves to an equally complex and impressive realm, the human brain, composed of approximately 86 billion neurons, each connected to thousands of other neurons, forming an intricate network unparalleled in the world known to us. The striking similarity between the cosmic web and neural networks is not just a beautiful poetic metaphor. It is a fascinating scientific curiosity that has prompted researchers to meticulously examine the quantitative similarities between these two astonishing systems. Could it be that the universe, with its billions of galaxies, is reflected in the complex neural networks of our brain? Are we, in some profound sense, a reflection of the cosmos itself, a miniature replica? Could it be that the grand design of the universe is imprinted in the very essence of our being, in every cell of our body? Do the same laws that regulate the movement of stars also govern the intricate dance of neurons in our minds? These questions, once solely the domain of philosophers, are now actively being investigated by scientists who are discovering connections that could hold the key to understanding not only the universe, but also ourselves. From the very dawn of human consciousness, we have been irresistibly drawn to patterns. Primitive humans gazed intently at the night sky, recognizing constellations and tracking the predictable movement of celestial bodies. They carefully observed the cycles of the moon, the changing seasons, and the intricate symmetry of leaves and mollusk shells. This innate ability to find order in nature is not merely idle curiosity. It is a fundamental aspect of our intelligence, the primary way we make sense of the world around us. As we evolved, so did our understanding of these patterns. We began to realize that these patterns were not mere coincidences, but were governed by profound principles and universal laws. The ancient Greeks discovered the golden ratio, a mathematical constant that can be found in architecture, art, and even the proportions of the human body. Mathematicians like Fibonacci discovered sequences of numbers that describe the growth patterns of plants and the spiral motion of galaxies. Natural patterns are not limited to static forms and numbers. They are dynamic, unfolding in time and space. The branching of a tree, the meandering course of a river, the swirling clouds, all obey specific mathematical regularities. In fractal geometry, these patterns exhibit self-similarity, meaning they look the same at any scale, whether it's a single leaf or an entire forest. In the modern era, our relentless search for patterns has led to truly revolutionary discoveries. The double helix structure of DNA, the astonishing world of quantum physics, and the butterfly effect in chaos theory, all reveal a universe governed by deep patterns and strict laws. These discoveries have not only significantly expanded our understanding of the cosmos, but have also shaped our technologies, medicine, and philosophical outlooks. But what drives this tireless search for patterns? Is it merely a tool for survival, or does it point to a deeper, intrinsic connection between us and the cosmos? Could our ability to recognize patterns be a reflection of the universe's internal order, a kind of cosmic signature imprinted in our very being? In the vast realm of scientific inquiry, where the grand mysteries of cosmic space intertwine with the intricate enigmas of human intelligence, the research conducted by Franco Vazza and Alberto Folletti stands as a guiding star of innovation. Their groundbreaking scientific works have opened new horizons in our understanding of the universe and complex neural networks, demonstrating astonishing parallels that challenge conventional perceptions of reality. At the very core of their scientific investigations lies a question that has occupied the minds of scientists and thinkers for centuries. Is there a fundamental connection between the structural organization of the universe and the neural networks located in our brain? Vazza and Folletti, with complete dedication, immersed themselves in a deep study of this issue, applying advanced technological solutions and improved mathematical models. Their research approach was largely quantitative, focusing on a detailed analysis of matter distribution in the grand cosmic web and on studying the connections existing between brain neurons. Through meticulous analysis of extensive datasets and the application of progressive algorithms, they revealed that both the structure of the universe and neural networks adhere to a similar pattern known as a power law distribution. A power law distribution represents a unique mathematical relationship where a limited number of nodes possess many connections, while the vast majority have only a few. This characteristic pattern manifests in various natural phenomena, ranging from the global internet network to the structure of social interactions.
Vaza and Folletti discovered that the same pattern is observed in both the cosmic web and the neural networks of the brain. The significance of this discovery is extremely profound. It suggests that the universe and the human brain share a common architecture, a universal structure that transcends scale and complexity. This interconnectedness is not merely a beautiful poetic metaphor, but a proven scientific reality, a kind of cosmic signature that manifests in the very foundation of existence. The innovative research of Franco Vaza and Alberto Folletti has ignited a bright spark in the scientific community. Their discovery of structural similarities between the universe and neural networks has opened new horizons, leading to a lively and productive dialogue among leading experts. Dr. Alberto Folletti commented on this event as follows: "Our research is just the initial chapter in a much larger story. We have demonstrated quantitative similarities between these two systems in terms of their structure. The architectures of these complex networks appear strikingly similar. Combining the efforts of neurobiology and astrophysics can significantly expand our capabilities for obtaining new results. The significance of their discoveries extends beyond mere academic curiosity. From a deeper understanding of dark energy to the development of artificial intelligence, the potential applications of this knowledge are truly immense." Dr. Alberto Folletti also added, "If we can convincingly demonstrate similarities between a network like a neural network and the structure of the universe, we can gain more detailed information about the universe and galaxies. This fusion of analytical tools from two completely different disciplines can contribute to accelerating the development of artificial intelligence or artificial neural networks." However, this research has also elicited certain responses outside the strictly scientific community. Some have interpreted the results to confirm creationist theories or to justify New Age views. Vaza and Folletti clearly and unambiguously emphasized that their work is based exclusively on rigorous scientific research and has absolutely nothing to do with either creationist theories or metaphysical concepts. The future of this scientific direction is filled with hope and deep curiosity. Both researchers express a sincere desire to continue an in-depth study of this area, delving even deeper into the comparison of these two extremely complex systems. They are convinced that the results obtained require further analysis using more sophisticated tools, and that the next steps will involve moving to a higher level of complexity comparison. As we delve deeper into the mysteries of the human mind and the boundless cosmos, we inevitably confront a paradox that has simultaneously captivated and perplexed thinkers for many generations. In the boundless expanses of the universe, where time and space stretch beyond human comprehension, lies a paradox that has puzzled philosophers and scientists: the Boltzmann brain paradox. This paradox, named after the distinguished 19th-century physicist Ludwig Boltzmann, delves into the very nature of reality and our fundamental understanding of consciousness. Boltzmann's original concept was rooted in statistical mechanics, which deals with the study of the probability of random fluctuations in any system. Imagine a limitless universe, permeated by continuous motion and chaos, where the smallest particles are in a constant, disordered dance. In this cosmic disorder, amidst an infinite number of random events, there exists an infinitesimally small but non-zero probability that these particles could spontaneously, entirely by chance, arrange themselves into a specific configuration, forming a self-aware brain. This hypothetical brain, appearing and disappearing in a fleeting moment, would possess full thoughts, vivid memories, and a profound perception of reality. yet it would lack a physical body and any world in which to exist. The paradox arises when we fully grasp the immensity and boundlessness of the universe. Over an infinite amount of time, given sufficient temporal duration, the random formation of such a self-aware brain becomes not just possible, but inevitable. This leads to a rather unsettling and disheartening conclusion. It is statistically more probable for a solitary, self-aware brain to spontaneously arise in the void of cosmic space than for our entire observable universe to evolve into its current complex and ordered state. The implications arising from the Boltzmann brain paradox are truly profound and raise serious concerns. If the probability of such a random brain existing is statistically higher than the probability of our entire universe existing, then what conclusion can we draw about the true nature of our own reality? Does this mean that our personal perceptions and experiences are merely illusions, fleeting fluctuations in cosmic chaos? Are we ourselves no more than ephemeral oscillations in the boundless ocean of cosmic disorder? This paradox has generated heated debates and deep reflections among philosophers, scientists, and thinkers from various fields of knowledge. Some researchers see it as a serious challenge to our established understanding of probability and the very essence of existence. Others perceive it as a metaphorical exploration of solipsism, a philosophical concept asserting that only one's own mind is the sole reality that can be known or that exists at all. Beyond the Boltzmann brain paradox, an even more fundamental and profound question arises concerning the true nature of consciousness.
One question that has intrigued both scientists and philosophers for centuries is whether the universe itself might possess consciousness. The idea that the universe is capable of having consciousness is by no means new. This concept has been thoroughly explored in various philosophical traditions throughout human history and has found a certain resonance in some modern scientific theories. Historically, the concept of a conscious universe has been strongly associated with panpsychism, a philosophical viewpoint according to which absolutely all things in the universe, from the smallest particles to giant galaxies, possess consciousness to some degree. This idea has been embraced and developed by certain Eastern and Western philosophical traditions, suggesting that consciousness is not merely a byproduct, but a fundamental and inherent aspect of reality itself. In the realm of modern science, theories that suggest the possibility of the universe possessing consciousness have emerged from a deep study of quantum mechanics. Some interpretations of quantum theory hypothesize that consciousness plays a certain role in the process of wave function collapse, implying a close interrelationship between the observer and the observed object. Cosmologists and neurobiologists have also actively explored this concept, striving to understand how consciousness might manifest on a truly cosmic scale. Theories such as integrated information theory, or IIT for short, suggest that systems possessing a high degree of complexity and integration could potentially be conscious. This leads to the very tempting and intriguing possibility that the universe, with its incredibly complex web of galaxies, stars, and cosmic structures, might possess a certain form of consciousness. The idea of a conscious universe remains a subject of active debate and continuous research, yet it is firmly rooted in the realm of philosophical and scientific speculation. While this concept prompts us to reflect deeply on our own place in the vast cosmos, and on the interconnectedness of all existing things, it inevitably enters metaphysical territory and therefore must be approached with extreme caution and the application of critical thinking. Having considered these speculative ideas about a conscious universe, we now turn our attention to a more grounded and scientifically oriented theory, Dr. Donald Hoffman's fundamental theory of consciousness. Dr. Donald Hoffman, a distinguished neuroscientist and philosopher, has dedicated his entire life to unraveling the profound mysteries of consciousness. His groundbreaking theory seeks to explain one of the most enigmatic and elusive phenomena in all of existence, the true nature of conscious perception. Dr. Hoffman's theory is based on the premise that consciousness is not simply a byproduct of complex computations occurring in the brain. Instead, he argues that consciousness is a fundamental aspect of reality, comparable in significance to space and time. Drawing upon principles of quantum mechanics, advancements in neurobiology, and profound philosophical concepts, Dr. Hoffman's theory explores the intricate interplay between micro and macro levels of existence. He hypothesizes that consciousness arises from the complex interactions of quantum particles within the brain, with these interactions governed by principles that extend far beyond traditional physics. Professor Hoffman's work has initiated a series of groundbreaking experiments and fostered fruitful collaboration among representatives of various scientific fields. His proposed theoretical concept has undergone thorough empirical analysis, employing the most modern technological solutions for a deep study of the phenomenon of consciousness. Although Hoffman's ideas have garnered significant support and admiration among many in the scientific community, they have also faced certain disagreements and criticisms. Opponents of this concept point out that its strong reliance on the principles of quantum mechanics, as well as its rather bold assertions regarding the fundamental nature of reality, undoubtedly require deeper confirmation and subsequent comprehensive research. However, despite these discussions, the fundamental theory of consciousness developed by Donald Hoffman represents an original approach to understanding consciousness that organically combines scientific inquiry with philosophical reflections. The interconnections observed between the immense universe and complex neural networks significantly transcend the boundaries of ordinary scientific interest. They open the gates to the deepest philosophical conclusions and carry broad implications for our entire understanding of existence. Such interconnections prompt us to perceive the cosmos not as a simple collection of isolated objects, but as a dynamic, tightly intertwined network of relationships. They serve as a source of inspiration for forming entirely new perspectives regarding the development of technologies, ethical principles, and our collective responsibility as conscious inhabitants of cosmic space. Questions concerning the study of the universe and the phenomenon of consciousness have remained a central problematic in philosophical thought for many millennia. From the era of ancient Greek sages to modern thinkers, the continuous quest to comprehend the true nature of reality, the meaning of existence, and our place in the boundless cosmos has constantly shaped human consciousness. Some scientists and philosophers tend to view the universe as a deterministic mechanical system, while others adhere to more mystical and esoteric views. The discovered interconnections between the grand cosmos and the human mind merely add an entirely new dimension to this eternal and ongoing philosophical discourse. The concept of universal interconnectedness is not merely a scientific observation or theoretical construct. It is, first and foremost, a powerful call for deep reflection and introspection. It strongly urges us to perceive ourselves as an integral part of a much larger whole, while recognizing the extremely delicate balance that sustains life throughout the universe. This idea compels us to transcend narrow self-interests and consider the potential impact of our actions on a much broader cosmic context. The path of future research undoubtedly promises many exciting and astonishing discoveries. Although the discovered interconnections between the immense universe and complex neural networks certainly generate immense interest, it is critically important to approach their study with maximum scientific rigor and impartiality. Erroneous interpretations and the pursuit of sensationalism can not only create numerous misunderstandings, but also distract from the genuine scientific value inherent in these crucial discoveries. This is precisely why let our insatiable curiosity serve as a reliable guide in the process of exploring the boundless cosmos, and our developed critical thinking help us stand firmly on our feet as we continue to delve into previously uncharted territories of comprehending and understanding the universe. Thank you for your attention, and we'll see you in the next video.